Hello everyone, myself Abhinav Gaur from NXP Semiconductor. So the topic of today's presentation in DVCon U.S. 2021 is metrics-driven sign-off for SoC-specific logic, commonly known as SSL, using formal techniques. The co-authors of this paper are Gaurav Jain and Ruchi Singh. Alright, so this is going to be our agenda for today. We will start with a basic introduction on the challenges of running formal at SoC level. What do we mean by a SoC specific logic, etc. We will then move to how we actually use formal in our day-to-day work, starting from planning to some of the infrastructure aspects. We will then move to slightly advanced topics like formal sign-off flow, regression flow, and metrics generation flow. And then lastly, we will discuss the key takeaways from this session. So let's start. Let's talk about the challenges in running formal at SoC. While formal is now increasingly getting used at IP level, at SoC level, verification engineers are generally a bit apprehensive. The common concerns are, will the formal tool be able to handle such a big design? Will my assertions converge at SoC level? Shall formal be used only to do connectivity checks at SoC? So all these are valid concerns, and they cannot be answered immediately. But at the same time, they cannot deter the users from being creative. So one must always remember that isolation and state space reduction are the golden rules to apply formal in any at any place. Keeping that in mind, let's discuss what is SOC specific logic and how applying formal on it can be advantageous. So as you can see in this diagram, it is a very simplistic representation of a SoC. So we have various masters as well as core on the north side of the interconnect, whereas various slaves and memories on the south side of the interconnect. However, I want you to focus on the yellow clouds, which represents the SOC specific logic, which are added as per the requirements of the SoC. While IP or subsystems are generally pre-verified in a standalone environment, SSL, come up directly at the SoC level because their requirement is dynamic in nature. And also it is quite difficult to plan for them upfront. At the same time, their complexity level is quite suited for formal in most cases. So what we feel based on our experience is that SSL is a good candidate for formal and it can help in accelerating the coverage. So now let's look at some of the examples of SSL. So for example, a logic that is added at the SoC level for compatibility between two IPs. General purpose registers. These are commonly added at the SoC level for miscellaneous controls. Then there may be some logic added to meet assumptions at the inputs of a given IP, because generally IPs are made in a reusable fashion, but the SoC requirements may be slightly different. So the design team might have to add certain logic to meet the assumptions of the inputs. Then there may be IP wrappers tuned to the need of the given SoC. So again, these can be termed as SSL. Synchronizers, blocks or pipes added to help the STA team or the physical implementation. Then SSL added for security or safety. Protocol size or conversion gaskets. Again, these are some of the examples of SSL. Getting 100% coverage on these using SoC level simulation tests is quite difficult, whereas the same can be done much faster using a standalone formal environment. Okay, so now that we know that SSL are a good target for formal, let's switch gears and talk about some of the planning aspects. As we all know, planning is a really important aspect of any kind of verification. In case of formal, it would be rather impractical to plan at the granularity level of properties. Reason being, it is difficult to anticipate the count of assertions, and also the plan would look really bulky if each assertion is captured separately. So this is what we propose. We recommend that the formal verification plan must consist of the design features to be verified. So as you can see, we propose that in the formal plan, we capture only the features. Features are linked to properties via a mapping mechanism. If all the properties linked to a feature are proven, only then the feature is referred to as pass. Otherwise, even one of the property linked to a particular feature is failing, we term it as fail. In case no properties are found associated for a particular feature, it is termed as absent. So this is just to give you a brief idea of how we handle the planning aspect in formal. We will talk more about formal features when we discuss the formal metric section. Now let's discuss some of the infrastructure related aspects for formal. We can divide our entire infrastructure into two parts. The common formal VIP, which is reusable across projects, and the SoC specific formal VIP, which is supposed to contain stuff that is specific to a particular SoC. So common VIP contains all the reusable components like makefile, tickle scripts for tool invocation, assertion package, scoreboards, assertion IPs, etc. Whereas SoC specific formal VIP contains setup specific assertions, tickle file for defining the clock, reset, black boxing of modules, etc. So this is just one way of handling it where we are making use of both the common and reusable part in a single entity called common formal VIP and maintaining all the SoC specific stuff in a separate VIP. Let's also discuss how a typical formal test bench to verify SSL looks like. So master and slave assertion IPs, or commonly known as AIPs, are plugged in at the master or slave ports as applicable to take care of the protocol related constraints and assertions. So because of these AIPs, the user need not worry about the protocol related constraints as well as the checks that are related to the protocol, and they can focus more on the actual functionality of the DUT. Some additional custom logic may be required to drive rest of the DUT inputs. So depending upon the sideband inputs or the input signals which do not follow a standard protocol, we may have to write certain custom logic, or even in some cases we may have to write certain modeling logic, so which can be used for coding the assertions in formal. Lastly, a separate assertion module can be coded which contains the properties specific to the functionality of the DUT. So these properties will be assertions, assumptions, as well as covers. So this is just a sample, example of how a formal setup can look like for verifying SSL. Okay, so now let's quickly touch upon some of the formal apps used for SSL verification. Automatic extraction of properties, commonly known as AEP, can act like a good starting point whenever we are starting on any formal setup. It is very, low effort intensive in setting up. Uh, it acts like a super linting type of tool, and it can report basic issues like overflow, underflow, array boundary check. And AEP can also be used to develop the initial set of constraints, which can then further be used in the FPV setup. So then we have the formal property verification, or the FPV app, which does the major part of verification. So I mean, this is the most extensively used app in general for formal. The requirements of the SSL, which come either as part of some spec or in some other format from the designers or the architects. These requirements are translated into properties by the verification engineers. Assertion IPs, again, they are helpful here. They can be used to handle the protocol related constraints and assertions. So we have vendor based AIPs for standard protocols like AMBA, whereas we have developed our own custom AIPs for NXP in-house protocols. Another commonly used app is the formal register verification, or commonly known as the FRV app, which can be used to verify the general purpose registers or the GPRs, which are very commonly added at the SoC level. So this app reads the IPsec based register XML to generate properties for each of the register fields so that all the bit fields of the GPR can be verified quickly. So now that we have talked about some of the commonly used apps for verifying SSL, I also wanted to quickly touch upon a very common problem that we face when doing formal verification, and it is that of convergence. So while every setup requires deep investigation to tackle convergence related problem, and it's a topic where a lot of work is ongoing. Uh, at the same time, there are some techniques which usually help. They can be helpful. So first one is the obvious one, which is can we black box certain portions of the DUT without losing the intent of the design? So again, these are subject to the condition that black boxing is possible for that setup. Without either losing the design intent or by modeling the design intent in some other way. If it is possible, then it can definitely help in reducing the complexity of the setup. Another way of reducing of tackling the convergence problem is by reducing assertion complexity. How do we reduce assertion complexity? We can avoid writing an end-to-end property if it is not converging, and split it into smaller properties. So in this given example, instead of writing a property from I to O, we can split it into two properties, checking from I to M and then from M to O. Again, this can only be done if there you can actually write a assertion at the point M, so it is subject to some certain conditions, but if it is possible, then it will definitely help. Okay, so then moving on, some structures like memories, counters, FIFOs are known to increase the state space, and hence it is better to replace them with formal friendly models. We can also make use of symbolic variables to reduce the complexity. So in this given example, the code that you are seeing, we had a formal setup where we had to do memory integration verification. So what we did was that we added an assumption to make symbolic underscore ADDR stable. Now what it does is that symbolic underscore ADDR can now hold any value, but it will remain stable for a given formal computational cycle. So using this, we were able to reduce our formal convergence time of the session. It was sufficient for the type of problem that we were solving, but again, it comes with a word of caution that any kind of symbolic address or restriction that you introduce should not reduce any checks that you are doing in your design. Okay, so now let's move to the next topic, which is formal sign off. So let's start with the very basic step first, which is property density. So property density is generally the first step which tells what all is getting covered in the cone of influence, or commonly known as the COI of the assertion. So as you can see in this diagram, the purpose of property density is to find out input, output, or registers that are lying outside the COI of the assertions. So they can be the very first targets which the verification engineer can identify using this and try to target them by either modifying their assertion or coding more assertions. Moving on, so next step generally that is performed is that of over constraint analysis. So a very common question that formal verification engineers have is that if my assertion is proven, is it really proven with all the legal stimulus applied? So generally we have under and over constraints both in case of formal setup. Incorrect assertions or incorrect constraints can happen because of lack of understanding of the design, or incorrect coding of the constraint. So all these are reasons due to which a constraint can be coded incorrectly. However, under constraints are generally considered relatively safe because they will always result in false failures. So if I do under constraining, ultimately I will get a false failure and I will have to add more constraints to make my property proven. But on the other hand, over constraints are generally considered more dangerous because we may get a proven property which has not covered certain scenarios. because of over constraining. So these, as you can appreciate that these are more dangerous scenarios. So here formal tools can help by identifying all the DUT code which has become unreachable because of the constraints that we have written. So, they have become unreachable because of the over constraining done by the verification engineer. So this kind of feature helps the verification engineer in fixing the constraints to avoid false proofs. Moving on. So formal coverage analysis is the next step, or generally we call it as the formal core coverage analysis. What it does is that it bifurcates the cone of influence or the COI into further two parts. So first one is the logic, which is used in actually proving the property, which generally we refer to as the formal core. And the second logic, which may be part of the COI, but is not actually required in proving the formal assertion. So as you can see in this given example, assert dollar $past A not equal to B. So in this case, the COI will contain both A and B, but the formal core will just contain B. So as you can appreciate that formal core coverage analysis is more accurate because it is actually telling you what is covered based on what logic is used in the proving of the assertions rather than just the COI. So in case of formal core coverage analysis, we can target various metrics like line, branch, and condition. Formal coverage reports should be generated with each design release instead of being a one-time activity. Extraction of formal coverage reports should be automated and coupled with the formal regression framework. So in this slide, you can see we have shown a sample table for formal coverage, which covers all the metrics for various SSL setups. So sign off criteria is that the overall score for each of these rows should be 100%. At the same time, if you notice the last row, which is the average, it provides an indication of the overall progress of coverage combined for all the SSL setups that may be running for a particular SoC. Okay, so moving on to merging of formal and simulation coverage. So in some cases, we intend to get coverage from both formal as well as simulation. In such cases, merging of coverage is important to make sure nothing is getting missed. For example, using the URG tool, we can merge the various coverage databases coming from simulation as well as formal to create the final merged database. There may be an optional requirement of a map file in case the hierarchies differ between the simulation and the formal database, because of the fact that in formal we may be targeting the SSL in a standalone environment. One important thing to note here is that toggle coverage of the SSL setup should still come from the simulation only. Because in case of formal, we are verifying the SSL in a standalone environment. So only the line, condition, branch, those kind of metrics can be targeted in the formal environment so that we are not missing out on the integration related bugs, which can only be caught at the SoC level simulation stage. Last but not the least, as part of the formal sign-off process, we must also qualify the formal test bench to make sure that no assertion is getting missed. So although you might be having 100% formal core coverage, there may still be a possibility that your assertions are not, there may be something missing in your assertions. So formal test bench analyzer or the FTA app automatically inserts artificial bugs in design and expects that at least one of your properties should fail. If for a given inserted bug, none of the property fails, then that inserted bug is called a non-detectable fault or NDF. The goal of running FTA is to catch all the NDFs and update your formal setup so that there are no NDFs. There may be some exclusion cases, but apart from that, in an ideal world there should be zero non-detectable faults. One must note that FTA is quite compute intensive, and hence, unlike formal core coverage, it is not really practical to run it with every design release. So we recommend that it must be run only on the major milestones of the project. Okay, so now that we have discussed the formal sign-off flow, let's discuss the formal regression flow now. So first question is, why do we even need formal regression in case of SoC? So as you know, design keeps on changing with every new release, and asking each of the formal setup owner to run these setups individually whenever a new design release happens would be a very unoptimal way of handling things. Hence, formal regressions must be run in a centralized fashion with each design release, and the entire process of launching regression to collecting the formal regression results must be automated so as to not, increase burden on the end owners of these formal setups. In an ideal way, they should only be notified if something fails for their setup in a given design release. So there can be two views for the formal regression results. In this slide, we are looking at the property-wise view, which is more like an engineering view, which shows for all the SSL formal setups, it shows the count of proven, falsified, vacuous, and inconclusive properties. Next one is the feature-wise view. So as we discussed in the planning section, all properties are linked to features and formal plans consist of features. So this view displays the same regression result, but in terms of passing, failing, and absent features. Okay, so moving on to formal metrics. Formal metrics are really important because using them, one can represent the overall progress of formal verification during the course of the project. Formal metrics can be represented in the form of two charts. First one is the week-wise progress chart and second one is the category-wise status charts. So let's look at the week-wise progress. In week-wise progress chart, x-axis represents the work weeks, whereas y-axis represents the percentage of formal features which are passing. It is pretty obvious that the end target is to reach 100%, and that is all planned formal features should be passing. The next formal metrics chart that we recommend is the category wise view, which provides detailed information on feature wise status per category. The green section represents passing features, red section represents the failing features, whereas difference in the length of the bar from 100% represents the absent features. So another important thing to note is that the generation of these metrics should be automated and it must be closely linked to the formal regression infrastructure. So one must not be, one must not try to attempt creating these charts manually because that may require a lot of effort. So the ideal way would be to use the formal regression results and create an automation to build these charts every week. Okay, so let's move to the conclusion now. So I have captured some of the key takeaway points from this session. First one is that SoC specific logic or SSL is a very good category which will give good ROI if we apply formal on it. Secondly, bug hunting using formal is always an exciting activity, but at the same time, verification engineers must also focus on the complete sign-off cycle of formal to ensure a qualitative sign-off. You know, writing and coding assertions is always, the thing that excites us the most, but we must follow, as described in these slides, we must follow the complete sign-off cycle to make sure that we are not missing on anything. Lastly, adopting formal metrics in helps in tackling the progress of the formal goals. Uh, to achieve the same, automation is a must to generate these metrics data. So with this, I conclude this presentation and I would be happy to answer questions now if any.